Pretty good, pretty good. It's very late in the night here, but good afternoon to all of you.
Yes, thank you, DK, for taking some time out of your sleep schedule for this. Appreciate it.
Yeah. So let me get started. So good afternoon again, everybody. Thanks to Gilad and Brian and Gabriel for inviting me to share some of the very latest things, what we have been doing. I hope next year we'll be able to meet in person. I think the HPC AI Advisory Council meetings are going in person. So today I'll be mostly talking on how do you design scalable middleware for HPC AI and data science. We just heard from Dr. Smith in one of his slides. He indicated like NCI is going for like a real hardware infrastructure to take care of this HPC AI and data science. So now the question is, how about the software, or how about the middleware which will run on top of this hardware to really give you the performance and scalability? So as most of us know, I mean, we are in a very exciting phase this year, especially 2022 has been very exciting because we have a real system which actually crossed the Exaflop barrier. We have been talking for the last 10 years how to reach that milestone, but now we have at least crossed it with the Oak Ridge Frontier system. If you take a look at not only the Frontier system, but all the Fugaku, Summit, all the systems, even whatever we heard from also Dr. Smith, we are heading into the commodity supercomputing. What I mean by that, we have commodity processors, commodity networks, commodity accelerators, SSDs, and all. So we are taking all these components. They are all different. They have all different features. You have CPU, GPUs. Now the DPU has come. So then the question is, how do we build the software stack? So that's what will be the broad challenge here. I'll be trying to answer this question. How to design high performance and scalable middleware for all these high-end computing systems while taking advantage of these heterogeneous resources, both on-premise as well as on the cloud. Now, if you take a look at the software architecture, any kind of communication library or middleware you try to design, the centerpiece is the programming models, because this is where the users are actually trying to use a model. For a traditional HPC, it could be the MPI or PGAS, even it could be CUDA, OpenMP, or some combination, MPI plus CUDA, MPI plus OpenMP. If you go to big data, it could be Hadoop, Spark, the new Dask is entering into that mix also. Or if you are trying to do some deep learning, it is TensorFlow, PyTorch. Now the question is, when people are trying to run their application with these models, they of course want performance. So that is at the top, but below we have all these different technologies which are being given to us, different kinds of networking technologies, multi-core, many-core architectures, accelerators. So I call this like below you can think of it as like a supply side. And then in the top is the demand side. That means the application kernels and the applications, the end users need that performance. So now the question is, how do we bridge the gap? And this is where the role of the middleware comes in. And not only the middleware which is trying to support the programming models, but how do you design the communication library and runtime? And this is where it goes into how best we can implement different kinds of point-to-point communication, collective communication, energy awareness, synchronization, I/O file system, fault tolerance, etc. Either you can do them in a layered manner, or you can also do co-design. And this is what in my group, we have been almost like working for 30 years with all the different networking technologies, coming up with newer kinds of designs. And not only we publish, but we also try to convert those into the actual middleware and then make those available. And that's what I'll be talking. So here again, to hit back the point that nowadays people are not just only running HPC or only running AI or big data. There is a synergy here. Many new workflows are coming up where you want to do might be computing for some part, then you do big data analytics followed by AI, or in any manner you go, and they're all dependent on each other. So now the question is, can we design convergent software stack? And because all these need actually, if you are trying to run on a let's say on a node with 128 cores with 16 GPUs, you need the scale up. Or 4,000 of such nodes, you need scale out. So any of these middleware actually need both the scale up and scale out, and same thing is also happening on the cloud. So what in my group we have been focusing on the recent years, can MPI-driven middleware actually be used for this kind of environment? We know MPI solves the HPC problem, but the question is, can the MPI substrate itself be used to provide this kind of a scale up or scale out for deep learning, machine learning, the big data, dask. So that's what actually I'll try to show, that we have concrete solutions where you can actually try to deploy our MPI-driven software stacks for the end users. So my talk will have these parts. I'll start with the MRP's MPI library project. Many of you might be familiar. If not, I'll introduce you. And here I'll try to give some insights on how we are trying to design this kind of high performance support for various CPU, GPU, DPU, and networking technologies. Then I'll go into the HiDL project, is a high performance deep learning and machine learning project. This is based on MPI. We have linked with the TensorFlow, PyTorch. And then I'll also be talking about the new accelerating deep learning with the DPU, the DO technologies. I'll also then go into the big data. That is a high performance big data project. Some of you might be knowing we've been working on that almost for 10 years. We did a lot of native design, like let's say Hadoop and Spark running over InfiniBand. But now, since there are a lot of these kind of choices in the market with respect to networking technologies, we are actually going a little bit up and using our MPI layer for the scale up and scale out. So in fact, I'll try to show something how you can directly run Spark over MPI. I'll also give an example of like how you can run data science applications with dask. And while we are working on these kind of solutions, not only we are targeting it to on-premise system, but also to the deployments in the public cloud. I'll give some examples of AWS, Azure, and Oracle. And on top of this, from the Ohio State University, we have all the softwares available. A lot of people use, but over the years, we have received a lot of requests for really providing commercial support. So in fact, we have been, for the last 5 years, we have been providing this commercial support through a commercial spin-off called Exascale Solutions, which is actually a sponsor also for this event, and also trying to provide value-added products. So I'll give a little bit of overview there and then conclude. So now if you take a look at a very high level, let's start with the HPC. We want to design on this exascale system, like let's say take a Frontier or the next generation machines, and then we want to provide some MPI plus X support. X could be as simple as OpenMP, or it could be a CUDA or OpenSCC, any of those combinations. You will come up with this kind of a list. We want very good internode, intranode performance. We need good collective communication, both blocking and non-blocking. We need to balance the internode and intranode communication, because these days, as the nodes are becoming very fat with a lot of CPUs and GPUs, there's a big challenge. And how do you balance the communication going in and out of the node? And of course, we need some support for multi-threading, good support for GPUs, accelerators, and we need fault tolerance, QoS, support for different hybrid programming, virtualization, and energy awareness. So in this context, let me introduce the MRP's project. If some of you are not familiar, we started this project almost day one of InfiniBand. It was InfiniBand, as many of you know, was introduced in October 2000, almost 20 years back. And prior to that, in my group, we were working on Mirinet, Quadrix. Those were the interconnects some of you must have heard of. And as soon as InfiniBand came, we were ready to jump in. And we had actually first open source version, the MRPich 1 at that time. We demonstrated it at Supercomputing 2002, almost 20 years back. But over the years, I mean, not only we have expanded that across all the different networks, Omnipath, iWarp, Rocky, even AWS EFA adapter. And recently, I'll talk about, we introduced support for even libfabrics, UCX. So now we support all the networks. We have support for Slingshot 11, Broadcom, Kernelist network, Rockport networks, and also all the different platforms, the CPU platforms, and also we have support for the DPU. And of course, the GPUs, both NVIDIA and AMD, and we are working on the Intel GPUs. So this software stack, I mean, we have been working almost now for 21 years. In my group, I'm very proud of my team. Even from academia, we are able to sustain this project for 21 years. And currently it's being used by more than like 3,000 organizations in 90 countries. If you go to the Evapis download page, there is a link tab called users. You should be able to see. And these are voluntary users. Again, a lot of people download, they don't want to identify themselves. That is okay with us. And just from our website, we crossed actually 1.6 million downloads just from our website. Of course, it is a part of the softwares are part of Red Hat, SUSE, OpenHPC, SPAC. A lot of people download from those sites. We don't keep track of these. But in addition, it's not just the download. I mean, it has been enabling a lot of top 500 clusters all over the world. And here you can see like how the release time and downloads are going up, especially for the last few years. We are on a very steadily rising curve. So this is where the architecture of the MHAPIS stack inside looks like. We have support for all the different networking technologies. Whenever a new networking technology comes with new features, this is where like the real interest lies. A lot of my students and staff jump into those features and see how to exploit those features. We actually publish these papers. And once we publish, in 6 to 9 months, we actually take these designs and push it into the MHAPIS stack. In fact, within my group, I think in some of the past talks I've indicated, we have almost like 200 servers in my lab continuously running QA test. And that makes like a real robust designs of the software stack. In fact, sometimes for some of the check-ins, we spend almost like 18,000 CPU hours or core hours to really go through all the kinds of the testing, performance regression, and also the functionality checking. And then we push this kind of a release. And the same thing we also do for all the different platforms. And at the top, we have the support for MPI, PGAS, and MPI plus X. And through that now, not only we support the HPC, but now we have been enabling the machine learning, deep learning, big data, data science. You name any of these upper layer stacks, we are trying to link that. So that actually enables people to use our library to do their jobs. So let me go into a little bit of details here of the MPI library project. So our latest stable release, which is stable and very high performance and very scalable, which is the 2.3 series. So this is where like we made this release in March. Then it brought newer support for Rockport networks, Slingshot 10 networks, and also very tight integration with SARP. So like this. And in August, this is a new series we have started. This is a 3.x series. And this is where now we have support for both UCX and leaf fabrics. So through that, you can actually run it over many other interconnects. Now we have support for even Cray Slingshot 11 over a Wi-Fi kernelless networks. They have the OPX, which is the newer version of the OmniPath drivers. We also support Intel PSM3 and also IBverse over UCX. So as of now, the 3-point series is just being developed. We'll have a new release in the next few weeks. We still advise for high performance scalable runs, still use the 2.37, and gradually in the next few months, we'll have the 3-point series totally feature rich, and then it will try to replace the 2.3 series. But if you want to experiment currently with any of these modern networks, you should be able to still run application. They may not be optimized, but you should be able to still run these things. So let me give some sample numbers just to illustrate. So this is like many of the deployments in the recent last year has been the AMD Milan plus InfiniBand SDR 200. So here you can see like in the point-to-point, we are able to give like around 1.9 microsecond. And within the node, it is actually 190 nanoseconds. That means there are 2 cores within the same socket. We are able to do MPI level communication of 190 nanoseconds. And of course, in the bandwidth within the node, we are able to go into 23 gigabytes per second. And outside, This is the STR200, so we are able to deliver very close to the peak, which is 23.5 gigabytes per second. So that is just an example of point-to-point, but as many of you know, especially MPI applications have this big need for collectives, and collectives are divided into blocking as well as non-blocking. So these are some of the numbers of the blocking, and these are actually, we have done some tight integration with SARP, which is the in-network computing environment from Mellanox. So here I'm trying to show like a MAP is to X versus the MAP is to X SARP, which is tightly integrated. And these numbers were taken on the Texas Advanced Computing Center, the Frontera. That is one of the largest CPU-based system with InfiniBand in the world. So we are able to run almost up to 8,000 nodes. And then as you can see, like these are like MPI barrier, MPI all reduce, MPI reduce with very tight integration with SARP. We are able to reduce the collective performance of like 5x, 9x, 6x kind of things. And of course, a lot of these slides will have these pointers to our papers. So please feel free to take a look. And many times in our design, we have very simple runtime parameters, just like any other libraries. So depending on what you have support underlying, if you have SARP running, you just need to turn on this flag, and you should be able to see these benefits. Now that is the blocking collectives, but over the recent years, there is a lot of focus on non-blocking collectives. So what does that mean? In the blocking collectives, if you see, like, let's say I'm trying to do all-to-all, think of like a 50,000 core job is doing all-to-all. Unless the all-to-all finishes, nobody's able to make progress. And of course, that leads to very inefficiency. So this is where the non-blocking collective started. So as you can see, like you can actually do the computation, and then you initiate the communication. So I can do the all-to-all in a non-blocking fashion, saying called I all-to-all. But then while the all-to-all is moving behind the scene, you can actually perform computation. So that means we can actually overlap computation with communication. So that is the whole idea of the non-blocking collectives. Of course, the applications need to be modified. Traditional applications most of the times have used only blocking collectives. And there is also a chicken and egg problem here because the non-blocking collective performance was not very good earlier in a lot of runtimes. So application people have not moved to non-blocking. But now I'll try to show some of the numbers, especially with the DPUs and all. We can have very good non-blocking collective support. So that provides a lot of incentive for end users to modify their applications. And when we put the modified applications together with our middleware, then you will be trying to see a big boost in the performance. And so this is the core of the things, like how do you exploit the overlap of the computation and communication for better performance. So here, what we have done, so there are two parts to it. The middleware needs to be modified, and then the application needs to be modified. So here we have done like a non-blocking collective support with SARP itself. So as you can see, like there's a blue is the MAP is to 236, the green is the 237, and we are trying to, if you take a look at the y-axis here, we have two of them. We are able to reduce the latency and also increase the overlap, and that's what we need. With the newer designs, we should be able to reduce the latency so that the non-blocking collectives perform very similar to blocking, but at the same time, we give you the overlap so that more and more computations can continue while the communication is going on. So I'll go into the DPU one in few more slides, but these are the pure CPU-based designs. So here again, it shows MAP is to on Slingshot 10. With CPU, we compared with other MPI stacks like OpenMPI and Cray. As you can see, these are like an intra-node. We are able to give like even 220 nanoseconds time. Inter-node is around like a 2.55 microsecond. And of course, you see the bcast all reduced. The steel line is our design. We are able to perform equal or better than the other MPI stacks. Now, this is the very latest. This is the Slingshot 11, as you know, which is being used on the Frontier system. So this is, we have enabled this support, MAP is to support. This is with our latest 3 series, 3.0. So you can see here, like we are able to deliver around 2 microsecond point-to-point latency for small messages, and bandwidth-wise, we are able to deliver around 24 gigabytes per second on unidirectionally, and then 42 gigabytes per second bidirectional. Okay, so if you have access to any of the like the Slingshot 11 and you'd like to experiment with it, please feel free to download our latest version and use those. Now, those are the CPU side, but now let's take a look at the GPU side. This has been there for many years. Some of you might have known of the terminology called CUDA-aware MPI. In fact, from my group, we introduced this concept at ISC 2011, almost 11 years back, with this concept, and now it is very widely used in a lot of stacks. So the idea is that if I have a GPU and InfiniBand adapter sitting in the next to each other on the PCI bus, most of the time, traditionally, you try to do, let's say you launch a kernel to the GPU, you perform the computation, but to perform the communication to another GPU, you typically do a CUDA mem copy, do an MPI send, other side you do an MPI receive, and then you do a CUDA mem copy. We proposed a change in the paradigm. Instead of doing all those so many steps, can we try to do like just specify MPI send from the send buffer, and then the other end you just call MPI receive on the receive buffer, and everything else will happen within this MPI library. Based on the message size, based on the destination, it will try to find out the automatic path. And here we actually worked with NVIDIA and Mellanox that time. There was a GPU direct RDMA design, GDR copy. So all those things we have actually incorporated into our library. And these days, actually on modern platforms, we can actually send data from one GPU to the other GPU in 1.8 microsecond using all these nice concepts. And that leads to very high performance and productivity. Now, those designs have been already there. So now we are trying to go to the next levels of design. So this is a new design which is coming up, which is enhanced derived data type support together with the UMR. This is the Unified Memory Registration Scheme from Mellanox/NVIDIA. We just published this paper at the Hot Interconnect conference in August. So as you can see here, like this is our the new design. These are like these are running the Milk application like Milk, NAS MGY. We are able to improve performance by 30%, 35%. So this design has not yet been integrated. It will be available in the next release. But another direction which we are working is the on-the-fly compression. This has been there in our very latest release. So the idea is that, again, use that CUDA-aware MPI concept. I can send data from one GPU to the other GPU using GPU direct RDMA and all those concepts. But if the message is very large, it still takes time. Okay. Now, if you think many times, like we do computation, we perform communication. So the question is, can GPU cores be used to do on-the-fly compression before I send the data? Okay, so if I have a 4 gigabyte, if I can compress using the GPU on the sender side and on compress on the receiver side, can I see the benefit? So this was the paper we presented at IPDPS last year. It was a best paper finalist. And we have multiple different compression schemes. And here I'm trying to show a real concrete example of an application level benefit. It's an AWP ODC, which is a seismic simulation. It was run on Lawrence Livermore National Lab, the LASM cluster with up to 512 GPUs. As you can see, with our compression scheme, on-the-fly compression scheme, we are able to boost the performance by 18%, 35% in terms of flops, and in terms of the runtime, reducing like 26%, 15% kind of things. Similar things now you can do. Instead of a point-to-point, you can redesign the collectives using this online compression. And that's what we have done. This is the all-to-all compression. We presented these results at ISC this year. And here again, you can see like this is a scientific application PHDNS. We are able to reduce by like a 29%. And this is a deep learning application using the deep speed framework. There also we are able to reduce the thing by 35%, because these are the applications which are dominated by all-to-all. And these are all available in our public release. The latest, we have the MAPIS2 GDR 237. You should be able to download and utilize these benefits. Similar kind of things, a lot of these networks nowadays, a lot of systems are being designed with multiple networks. One such example is the DGX2 A100. So since multiple rails are there, so now how you can use the CUDA-aware MPI together with these multiple rails. And that's what we have done here. You can see some numbers compared to Nickel library. We are able to deliver better performance for collectives on these systems. Now, similar, that is the all-to-all. We have done very nice designs optimizing on all-to-all V because a lot of applications also use this all-to-all V. And here you can see across a lot of different MPI libraries, across different systems, we are able to give you performance. This is we are running an Hefty library, which is from Oak Ridge and University of Tennessee. We are able to boost their performance by almost factor of 5, factor of 28. And again, this design is already available in 237. If you have an application with all-to-all V, you should be able to see the benefits. So those are some of the NVIDIA results. We have been providing the support for also AMD GPUs for last several years, together with the HIPification process. So here you will see like this is running on the Lawrence Livermore National Labs Corona cluster, compared to like a or MAPIS to GDR and OpenMPI. We are comparing, as you can see, like for some of the collectives, we are able to do far better compared to the other libraries. The same thing also, you can see now the Slingshot 10 plus GPU. I showed earlier the CPU results. GPU results are very similar. We are able to use that CUDA-aware MPI concept together with the Slingshot 10, both for the point-to-point as well as for collectives. And as you can see, sometimes for the collectives, we get significant performance, even in fact better than also RICL version. Now let me go into the DPU. So those are some of the numbers I showed with the GPU, but DPU is bringing another dimension. As many of you know, like we have CPUs and the Bluefield DPU from NVIDIA not only has the RDMA engines, they also have set of ARM cores. So I call like a executive and assistants. So just like in the real world, you have set of executives and then you have assistants. So we are trying to see how to offload MPI level functions. That is the communications, how we can offload. Later on, I'll show how you can also offload computations. Okay. So here, especially, we have taken this focusing on the non-blocking collectives. You remember a few slides back, I said non-blocking collective is becoming more important. That provides the overlap of computation communication, and DPU technology is very ideal for that, because while the hosts or the executives are performing the computation, we can actually offload the communications to the DPUs. So we have a library now called MHAPPIS to DPU. In fact, this is being designed by the Exascale solutions. I'll show some results. If anybody's want to try this out on a DPU cluster, please send a note to this address, and you will be able to get a trial license. Now let's take a look at some of the numbers. So this is the OSU non-blocking all-to-all. That is the standard benchmarks from the OSU micro benchmarks. Many of you are familiar. Typically, what happens, the MPI protocols, if some of you are familiar, like the short messages go through copying and the large messages go through rendezvous. So short messages in the basic any MPI stack, you will see some overlap, but it's very little. Whereas for the large messages, you don't get any overlap because you do RTS, CTS, those kind of activities. But with MAPIS to DPU, as you can see, we are able to push almost 100% overlap. Okay, so that is very ideal. So so that you can have overlap of computation with communication. So then this is that is the overlap capabilities. But now if you take a look at both computation and communication, that is the most important part, not just the communication. Now, if you see compared to the basic MAPIS 2 DPU is able to improve the non-blocking all-to-all by almost 22%, 21%, depending on the message sizes and all. And this is a 512 process run. This is a 1000 process run. And now that you can actually try to translate into the application. So this is we have been working with a P3DFFT. That is one application from SDSC. So they have actually taken the blocking version and changed to non-blocking. And this is where we try to actually now modified P3DFFT is running together with our runtime. And then at an application at the kernel level, you can see that we are able to give you like a benefits of 21%, 18% for different grid sizes. So it is the same hardware, but we are able to give you much more higher benefits with respect to the modified software. So these are like some additional examples. Like here, if you see some Oak Ridge, people have done some studies on Summit. You can see how MAPIS is performing better than other MPI libraries. There's also another institution called Idaho National Lab. They use a lot of applications like Moose, Betsy. In fact, they have been continuously using MAPIS2. And in fact, this was a presentation by INL at our MUG annual conference we did last month. So what they showed that in the right-hand side, these were all their users were using different libraries over the years. But beginning of this year, most of them have moved to MAPIS2 because MAPIS2 is actually delivering the far better performance and scalability compared to others. So that is kind of an overview of the MAPIS project. Let me quickly move into the machine learning, deep learning. So what we have done here, a lot of people want to program at the top layer, the TensorFlow, PyTorch, and MXNet, but how do you provide that scale up and scale out? So this is where different frameworks are coming up, like Horobot, Torch Distributed, DeepSpeed. So we have actually linked to our MAPIS2 library. So what it means that as an end user, you can still use your frameworks, TensorFlow or PyTorch, but the performance will come from the MPI library. Okay, so this is the project we call like a high DL, high performance DL. We have, if you go there, it has a very detailed guidelines on how to build this software stack yourself. So let me show some numbers. So using this framework, so this is like a showing data parallelism, pure data parallelism on CPU nodes itself. As you can see, like we ran it on Attack Frontera, almost 2,000 CPU nodes. The restant 50 we were able to train just in 7 minutes, purely using the CPUs. These are some examples of GPU-based training. Here we compared to our MAPIS2 GDR design with Nickel, and we were able to deliver, in fact, higher images per second with our MAPIS2 GDR. So then what we have done, a lot of these days, the model sizes are increasing in size. So if you take like a ResNet 1001 and all, sometimes these don't fit within the GPU memory. So we call it like out of core. So we are trying to provide those kind of out of core training with a newer framework called hybrid parallelism. Both data parallelism as well as model parallelism. We presented this at ISC 20. And here you can see like we get very good performance. Like on 512 nodes, we are able to give like a 481x speed up with a very good scaling efficiency. And the model parallelism itself, one can use to even get better performance. So here we have running these experiments on 1,000 GPUs on Lassen system. And here you can see we are able to run with almost like a 97% efficiency. Now, not only we are able to show the basic level, like you can enhance the training, we are actually working with some of our like a pathologist. This is a very concrete example. We are working with a pathologist at the Ohio State. So they were trying to do all these called whole slide images. And if you take like each of these images, like 100,000 by 100,000 pixel, they cannot fit into a single GPU memory. Typically, they try to do tiling, but if you do tiling, you lose the accuracy. So when we started working with them, they had that model. They were running it on only single GPU. It was taking 30 hours. And we actually parallelized it to run it on 128 GPUs with only 0.46 hours. So that was a significant reduction in the training time and as well as like improving the throughput. So those are like a concrete example of deep learning, similar thing which we are doing for machine learning. Some of you know about QML. So here we have done a QML tight integration with MPI for Pi and with the MAPIS2 GDR. So now you can actually release, we have a QML release here. And if you take a look at like some of the common machine learning applications like k-means, linear regression, nearest neighbors, we are able to compare to like the Nickel library approach, the MAPIS2 GDR library approach is giving you like almost 1.6x improvement in the execution time. So that is with we have done the GPU. Now think of like a DPUs. Now how we can utilize DPUs for accelerating the deep learning workload. So if you take a look at the training, typically you have multiple steps: data augmentation, training, model validation. So what we have done, we have come up with this offloading strategy. This paper was presented last year. Training process can run on CPU, data augmentation can run on DPU, testing also can run on DPU. So we are trying to, since the DPU processors are not that powerful, we're trying to balance out what can run on CPU versus what can run on DPU. So we have actually, is the similar to MAPIS2 DPU, we have an Exascale AI DPU package. And I'll show some numbers, and any one of you are interested, you can send us note for a trial license. So here, if you see, like this is a ResNet 20v1 model with a CFAR 10 data sets, we are able to get around 17% benefit. It's exactly the same hardware. We are trying to exploit the DPUs to give you that boost in performance. And this is the ShuffleNet with a tiny ImageNet data set. We are again around getting around 13% improvement. So then let me quickly move to the big data project. This project has been going on very long, starting with 2013. So we did a lot of work on like taking basic Spark, Hadoop, Kafka, HBase, everything to InfiniBand. So all these things have been very widely used. You can actually download. But then what we are seeing recently is that because newer and newer networking technologies are coming, it is taking a lot of time to really redesign for each and every network. So this is where we have started moving into that MPI layer. Here, this is a number of RDMA Spark. This is the direct design. Compared to IP over IB, you can see RDMA. We can give you like a 37%, 43% benefit. But this is the very latest design. What we have done with the Spark, within the Spark, there is this NATI. We have directly taken that NATI to the MPI communication library. Okay, so we are going to the up to MPI. And as earlier we saw, like MPI supports all the different networks. So now Spark can actually run on any of these networks. So now you can see some numbers here. Compared to the earlier design, like the Apache Spark, we can give you benefits. Even compared to our earlier RDMA Spark, we can also give you benefit because now we have more optimizations and all in the API layer. So these are like a group by test, sort by test. This is another like a using InfiniBand 200 gigabits, similar kind of things. We are able to reduce the time by factor of 3, factor of 1.3. This is a weak scaling evaluation, very similar story. We presented this actually last month, just a few weeks back at the IEEE cluster. Similar thing also we see with Intel High Bench. So this is the new direction we are going. We'll be making a new release. Just wait for another, might be 2 or 3 weeks. You will see this new release. So you should be able to run any of the Spark jobs on top of MPI library. Now, the other thing which is emerging is, some of you know, the Dask. So this is where that is for like the data science application. So we are again going through a very similar approach to provide the Dask supports with MPI. And this we presented last year at the CC Grid. So we have this MPI for Dask. This is trying to show some numbers. You can see like a QPy array and its transpose. We are able to, compared to IP over IB and UCX layers, we are able to do even better than 3.47x, almost 6.9 kind of performance benefits. So these are like some of the sample numbers on the on-premise system. So gradually we are trying to take it to the cloud because a lot of people want to use our stuff in the cloud. So we are working with all 3 major cloud providers, AWS, Azure, and Oracle. As many of you know, Azure directly, their HPC instances use InfiniBand. So all our libraries can directly work in a transparent manner. So in fact, once we make the releases, Azure takes and then make them available. For example, the latest they have included is 236. They were working on the 237. On the AWS side is a little bit different story because they don't use InfiniBand, but they use this elastic fabric adapter. So what we have done a very native design on top of EFA adapter. We made a release in August. This again, we took the very latest 237 and then moved to that library. We also have the MVPs 2.3 series with leaf fabric support that can also run, but it will not give you the best performance because it is going through the leaf fabric. So if you take a look at some of the sample numbers here, because we are able to go to the EFA layer, these are the numbers on the ARM Graviton. And as you can see, as the number of nodes increases, we are comparing our earlier design with optimized design and OpenMPI. We are able to give you far better performance as the system size scales. On the Oracle side, they use the Rocky. Again, since all our libraries support InfiniBand and also Rocky, they can also work in a transparent manner. Here you can see like a mini AMR application. We are trying to see compared to HPCX and Intel MPI, we are able to in fact give even the 4x performance benefit. So these are the cloud results. So that means if some of you are using cloud, you should be able to directly utilize our software stacks and then get the same benefits on the cloud as well as you are getting on the on-premise. Now, with this, let me try to wind down. So as I indicated earlier, like from OSU side, we are able to deliver all these solutions, but a lot of people want real commercial support. And this is where these Exascale solutions, which is the commercial spin-off, has come. And through that, we are actually providing, just like any commercial software stack with a service level agreement, with optimizations, tuning, we are providing support to many national laboratories and international HPC centers. And as we are doing those, people have been asking a lot of value-added products on top of whatever we have from the OSU side. So we have like a packages like Exascale HPC, Exascale AI, which is basically that ideal framework. You don't have to build on that. We have like a build ourselves. So you can just download and install and get far better performance. And also like I indicated about this MHAPIS2 DPU and Exascale AI DPU. So with this, let me conclude what I presented here. We started with a very high level overview of the Exascale systems and the cloud. And I motivated the need that if you want to design the software stack, you need to take a holistic view of HPC, big data, deep learning, machine learning, data science, and also the computing continuum. I didn't talk much, but we have been working like starting from edge to HPC kind of things. That is the new environment is coming. And I showed some of the solutions, especially MPI-driven solutions, so that all these stacks can actually benefit from the underlying MPI layer, both scale up and scale out. And it will also allow you to mix and match any of these kind of the domains in your workflow. And as we see, like continuously newer and newer technologies are coming. And of course, it needs continuous innovation. And that's what we've been doing in my group for the last 30 years. And this is just a shameless advertisement I'm doing since we have done a lot of like a big data, high performance computing. In August, just last month, we have a new book which has come out by MIT Press. It actually shows how these fields are coming together, where the state of the arts are, what are the solutions, and what are the next set of challenges. So if you are interested in this field, please feel free to take a look at this book. I'd like to thank all my sponsors. As I indicated, these projects we have been running almost InfiniBand-based project running for 20 years now. I would like to thank all of them, but more importantly, these are all my heroes. A lot of students and staff. So what I presented here in last 45 minutes is actually work of 20 years. So I would like to really salute to all of them. With this, I'd like to say thank you to all of you. If there are any quick questions, I'll be very happy to answer.